Hi there, this is a quick introductory session to R and Rcmdr. Just to get everybody started, I'm going to go through pretty quickly, so you can use the pause button or the rewind button on your video viewer if you happen to miss anything. So the first thing to do is to start R. You'll need to go through the menu and so forth, which will be different from mine, so I won't bother. I will start it up from the button that I have on my taskbar there. Okay. So when we first open R, we get a window opening, which doesn't really tell us much, and that's one of the frustrations of using R, at least in the beginning. You don't get a lot of feedback from it, particularly when you do things correctly, which is kind of strange. So what we're going to do is load a package, and we're looking for a package called Rcmdr, or abbreviated to Rcmdr. So we'll highlight that. So we've clicked on Packages, Load Package, select the one we want and click OK, and it will think about it for a while, and then it should pop up another window which sits on top of R, which is our Rcmdr window, and here it is. Okay, so that's Rcmdr. We'll just maximize that to make sure we've got it, and if we look back at the R window, we can see that we loaded a bunch of other statistical and other packages that make Rcmdr work, right? So what do we do? At the moment, nothing. We have no data. So what we're going to do is to go to LMS. Mine looks a little bit different from yours. Don't worry about that. And you'll see an entry on the menu on the left, Practicals Data Analysis. And there's a bunch of different entries corresponding to the different classes we have. You might be interested in looking at some of these things later on, but we're going to click on Getting Started, which gets us into that folder, and after a blurb on how to use it, which feel free to use, we've got a data file, the Hubbard Brook data from a long-term ecological experiment in the USA. So if we click on that, it will open up a little box which lets us make a choice about to open it in Excel, which is not what we want to do, or save it somewhere, which we do. So we're going to accept, save it, click OK, and we're going to find a place which I already have open. It's a folder I have called Practicals ENVT3361. You may or may not have or wish to create one like that. Doesn't matter, you just need to put it somewhere where you can remember it. That tells us what sort of file we've got, and we're going to save it here, although I already have one, so I'm going to pretend that I saved it and just cancel that. Alright, so we've got that in, and we can go back now to the Rcmdr window and do a couple of things to help us use that. The first thing to do is to set the folder which Rcmdr always looks in for stuff in this session. So change working directory, and I'm going to go and look for the folder that I want. I know pretty much where it is. It's in 3361, and it's the folder that I just saved that file to, and click OK. Now, there are other ways to do this, but you can see that it's generated a command or function with an R, set WD or set working directory, and it's done that. And now I can import the data. So I'm going to click on Data, import data from text file, because that's the format of data that we have, a comma separated values text file, and we're going to keep on going from there. Okay, I'm going to give the data set a name. It's from the Hubbard Brook Valley, so I'm going to call it HV1 for want of a better name. Keep them short because you sometimes end up typing them a few times. The fields are separated because it's a comma separated value by commas. It's from my local file system because I'm going to go looking for it on my computer, and I don't change anything else. The decimal point character is still a full stop or period, not a comma. So don't change the bottom there. And we'll open a file open window in the folder that we've just told it to look, to set our default folder, Practicals 3361. And there's my file. There's one I downloaded from the site earlier. They're actually identical. And open, and it opens that. So it generates a bit of script, which tells us what it did. It put into this object, which we've called HV1, the output of this function here, reading a table with a certain set of parameters. the separator being a comma, being the most relevant bit, comma separated values file. It's echoed back that in the output, but it's telling us that the data set has 200 rows or 200 observations or sites or samples or whatever they happen to be in our data set, and 24 columns, so 24 different types of information which we can have a look at using the View Dataset button there. Okay, so we can see first of all that we've got our 200 rows given by the leftmost column, kind of like a spreadsheet row number. It goes up to plot number 400, so obviously each we don't have 400 rows, so each plot's not represented, and that's our first piece of information. We've got a couple of what I call factors here. Now, factors are categorical columns in our worksheet, and they can take one of a number of fixed values depending on the factor. So this one is called relative to brook, and it can either be north or south of the brook, so it can only take two values. The next column is called transect. The samples were collected on a whole lot of north-south transects, so each transect's got a unique easting value, so we've just named it according to its UTM easting value, so it can only take a few fixed values of that. And the rest of the columns contain variables. Okay, so they're information which can take a continuous range of values, like pH can be anywhere between, in soils usually about 3 to 10, but it can be anywhere between those values. It doesn't have to be fixed at any particular value, such as this one, which must be north or south. That's a factor. This is a variable. So is moisture percent, gravel percent, sand, silt, clay percent, and so on. And we can scroll across and see that we've got a bunch of textural data plus some chemical data for soil sampled in this catchment. So the textural data up to silt plus clay, then percent organic matter, and calcium, magnesium, and so on in milligrams per kilogram. Right? And just one other thing that's worth looking at in these data, the existence of these sort of things. So when data are not available for any reason, we lost the sample, or we couldn't do the analysis, or there's not enough calcium in there to get a reading, we can pop this value in, which R recognizes as a missing value. So it's good to remember that. So it's uppercase N, uppercase A, no dots in between, not lowercase, not any combination, no slash in between. Otherwise R doesn't recognize it as the missing value code. Alright, so that's what the data look like, rows by columns, each column being a different type of information, and each row being an observation or sample number. So we can close that. And then we have some fun doing some stuff with the data. Alright, so there are a few things that we can do. First of all, under the data part of the menu, we can have a look at the variables in the active data set. So if we click this one, we get it. It's a good way to check that we read in what we thought we'd read, doing in simpler form what we did when we saw View Dataset. Or we can even calculate new variables. R's pretty good at being a calculator as well. Does things a slightly different way from we use in Excel, for example. Let's imagine that we've got a concentration of aluminium, but we're interested in the concentration of aluminium plus iron in our samples as a new variable. So we could do that. We could go Al plus Fe is equal to Al, and the mathematical version of that is Al plus Fe. And click OK. And the message tells us that we've got an additional column, and if we ran our names command again, and we can do this simply by putting our cursor in that line now and clicking submit, we've got that variable popping up in our list that we didn't have before. So we've created a new variable, which is aluminium plus iron concentration. What it might be useful for, who knows, but we can do that, and we can do a whole lot of other sorts of mathematical manipulations of varying complexity. We can do log transformation, we can raise things to a power, we can have very complicated mathematical expressions in there if we want. Alright, so that's data. Statistics we can look at. We can do a few different types of summaries. We can summarize the whole data set. Let's do that. It'll ask us, do you really want to do this? 25 variables in it? Well, it might be an issue if we had hundreds and we didn't want to see all that output. But it's worth doing. It's another good check to see that things are read in properly, because we get minimum and maximum values so that we can quickly see whether we've got any weird, like, negative values in there or something, or mean or maximum values which look too high or too low or whatever. And we can also check whether things have been read in as numbers, in which case they'll have minimum, median, mean, first, third quartiles and a maximum, or whether they're factors, in which case we get the categories and the number of samples in each category, in this case relative to the brook, north or south, and roughly the same number in each transects. Each transect's got roughly 30 or so values in it. If there are a lot of categories, as there are for transects, there are more than about 6 of them that will not display everything, but it looks like there's probably only one other category here, each at a different value of easting. Okay, so everything else seems like it's numeric, which is good, and it also tells us that we've got those 2 missing values for calcium, so that's potentially useful too. Alright, so statistics, summaries, and there's a bunch of things we can do in there. There are a few things we'll have a look at in later pracs, including correlations and tests of normality, whether our variable is normally distributed or not. The Shapiro-Wilk test is a test of preference there. We can compare means, for example using a t-test, or analysis of variance, and we'll spend a session looking at that. We can check whether our variances between groups are equal or not. Generally we would use Bartlett's test to do that. We can fit models to the data, most commonly linear regression, and we can do some quite sophisticated analyses like principal components or cluster analyses on our data if we so choose, but we won't go into that in this unit. One of the more immediately rewarding things to do when you're learning R is to create some graphs. I'll just show you a couple of examples how we might do that. For example, a histogram, so showing the distribution of a variable in numeric slices or categories. So let's look at the one that we just made, for example, and without selecting any further options we can just click apply on that, and we get a graph, a histogram of this aluminium plus iron content, which ranges from about 0 to 100,000, with a central tendency about 40 or 50,000, in this case milligrams per kilogram. Alright, now you can change some of the options in there if you like. For example, we could, instead of having R choose the number of slices it chops up the numeric values into, we could say, well, let's make it 15, and we get a slightly different graph with a bit of a finer resolution of the values, but we're still getting much the same information, the same shape of distribution, if you like. Alright, so we can do histograms. That's all very well. One of the most common that you'll use is to look at scatter plots or XY plots of the data. So let's pretend that we know something about the catchment. Well, I do anyway. So let's, as our X variable on the horizontal axis, let's choose easting and see if I know that the stream runs roughly from west to east. Let's see if something like coarse sand changes in its abundance from going from upstream to downstream, from west to east. And apply. What we'll get is actually not a very attractive looking graph, I must say, because it comes with a whole lot of information that we may not necessarily need. For example, this solid red line is a smoothed trend through the data. The solid green line is the linear line of best fit, or the regression line through the data. That can be useful to include, and the dotted red lines around are the range, if you like, or around the smooth line. What we can do is go back and under options turn those off. So we turn off the smooth line, turn off the spread around the smooth line, but keep the other stuff because it can be quite useful. And apply that, and we get a much cleaner looking graph. What it seems to suggest at this point, without analysing it statistically, just visually, we've got an increase in the amount of coarse sand as we travel east or downstream. Does it make any sense? We don't really know. We'd have to know whether the samples are influenced by the stream or not, and whether that trend in fact is significant, and which it may not be given the spread of values around it, and we'll show you how to do that in another session. Alright, so we can make quite nice graphs, and we have the option, for example, to change the titles as well to make it look a little bit more attractive. So the axis label could be something a bit more informative, and so on. So apply that and go back and look at the graph, and so we can start to tidy up some of the text and stuff on the graph. We can make those symbols larger or smaller. The plotting characters, the point size can be a bit bigger. Let's make them 1.5 times the size and go back and have a look. So we've got bigger plotting symbols. If we know a little bit more about how it works, we can actually, if we don't like a circle, we can use something else, and so on. The box plots tell us something about the distribution of each variable, whether it's skewed or not, and whether it has any outliers. And the plot itself tells us something about whether there are any unusual values identified by row number. As we can see for row 136 and row 86, they seem to have unusual coarse sand contents for some reason. And there are mathematical procedures that are used to detect those. So there are a bunch of other graphs you can use, and if you want, you can have a look at those. And it's up to you to explore and play with R. There's nothing wrong with learning by playing. I would encourage it in this unit. There's not a lot we can do to break things. Just be careful that we don't lose any real data. The stuff on LMS, of course, is pretty safe, so we can't break that. Alright, so we'll leave it there for now.